Okay, this is section 7.5, begins on page 419. Applications of the integral from science and statistics is what that should say, but we're studying integrals, so applications means applications of the integral. Science and statistics, first thing I want to remind you of, and some of you, not very many, not as many as usual, thank goodness, on the quiz, still don't fully understand what the integral can do for you as far as work goes. In physics, work is equal to force times distance, but that is only if the force is constant. Forces are never constant. Even if you're doing something as simple as pushing a box, something heavy across the room, right? When you first start on it, your force increases and increases until you start to move it. Then it stays steady, probably while you're moving it, unless you encounter some other friction or something slick. Then your force will back off. Otherwise, you fall on your head or you get stopped and you have to apply more. So the force is never constant. And when you get it to where you want it to go, you back off and it sits there. And all that time, your force is Even when you're taking your steps and moving along, you have one push from one leg and back off before the other leg takes over. The force is constantly, it's never the same. So this isn't really true unless you're doing something where force is constant. I don't know what that would be, but work is force times distance. You have to move something someplace for there to be any work done at all, because if this were zero, of course, you'd have zero work done. Forces, you gather those together, and this is the gatherer of forces. Work is equal to a gathering of little tiny forces and distances that resulted from that, and this adds them all up. This would probably be from the distance from 0 to 5 feet away or whatever like that, and then this would tally up all the forces. If you had a function that represented the variation in the forces, this would be that function. You know what I'm saying? This would be the gatherer of all the little stripes that you painted in underneath that function. We'd gather them all together and give you an area, which would be work.
And that would be total force used?
What's that?
That'd be like a total amount of
Well, it would add up all the forces times the little distances that you moved it. This probably would be better if we said X here. Work is force times distance, which we'll call X. This is little teeny weeny distances. Forces times the distance that force moved. And then the next one over, the very next one over might be a different force. And you move it a little bit. And another force, you move it a little bit.
Yeah, I get that.
Okay.
What the integral gives you work does.
The integral gives you the total work done by gathering all the little force times distances and adding them up.
And then work is just total force used, or what?
No, work is in foot pounds or joules or Newton meters.
Okay.
Because that's newtons, this is meters, this is pounds, this is feet, foot pounds, Newton meters, joules.
Okay.
Work is it's a funny quantity, but it involves force. Anyway, this is the key to this idea of gathering forces that are not constant. Okay, it's the idea of doing one of the first questions. Well, example one's really pretty easy. We're just gonna try it. We're just gonna show you how this works together. It says, find the work done by a force, which is, they're giving you the force equation. It's the cosine of pi x. If the force is the cosine of pi x newtons along the x-axis from 0 to half a meter. So that's a varying force. And so to figure out the work done on this one, we would say it's the work from 0. Work is equal to the integral from 0 to a half of the cosine of pi x dx. This is your forces, and the force is varying according to this function. That's your little distance that you're moving it. This will gather them all together and give you the area. We don't actually have to do this if you don't want to, but we would antiderive this and multiply by 1 over pi because of the chain rule. Don't forget that. Right?
Yeah.
So it antiderive that, and it would be sine of pi x times 1 over pi, evaluated from 0 to a half. What's the sine of a half? What's the sine of pi times a half? That'd be pi halves. That's 1, right? So the first one is 1 over pi. What's the cosine, or if I was busy trying to do this, it's not that, it's pi x. So there we go, half of a pi, that's what I mean, half of a pi is pi halves. Sine of pi halves is 1, and 1 times 1 over pi is 1 over pi. Minus, plug a 0 in there, you're gonna get the sine of 0, which is 0. So the answer is 1 over pi, that's how much work was done. That many joules of work, not much. Okay. It's just a sampling of that force times distance, and the integral gathers it together. Now we're going to get into the nitty gritty. Example 2 seems daunting at the first reading. We'll take it in pieces and maybe we'll get it. Please, after we read what's going on in example 2, do not turn the page. Let's see if we can figure this out together. Show you how to pull it apart in little pieces. Where are you going?
Yeah.
Which curricular work hurt? Okay, here we go. Example 2. Hurry up and get out of here so I can move on. Gosh. All right. So, example 2. This is a very, very cool problem. But there's a lot to it. So pay attention. Stay with me. One piece to the next. Here's the scenario. We have a leaky bucket that weighs 22 newtons when it's empty. That's a weight. Measured in newtons, we're not used to that, we're used to pounds, but it's 22 newtons when it's empty. That's what it weighs if you put it on a scale that measures in newtons. It's filled with water, and the moment that it's filled with water, they begin to lift it from ground level at a constant rate to a point that is 20 meters above the ground by a rope weighing 0.4 newtons per meter. The bucket starts with 70 newtons, that's how much the water weighs, approximately 7.1 liters of water, but it leaks out of the bucket at a constant rate and just finishes draining when it reaches the top. So, your simple task is to find the amount of work done. Well, and notice the questions are asked to help you bust this up. It says, what is the amount of work done lifting the bucket by itself? If we were just going to lift the bucket and that's all, not even with a rope, it was just going to be lifted up. Okay? We want to find out the amount of work done lifting the bucket. We want to find the amount of work done lifting the water. So we'll consider only the water that's in the bucket, not even with the bucket wrapped around it, just the water. And then we will lift the rope, figure out how much work is done lifting the rope. And then the deep part would be to add them all together. The work done for each piece. Okay, so we are lifting against gravity. So that's the reason why the weight is there. We got mass times gravity, which gives us weight. So here's my bucket. Here's the scenario I'm going to draw here for you. We got this going on. We got this big, huge thing like this and a pulley at the top. And the bucket's down here right at first. The water's in it like that. We got a hook around this right here. And it's going to go up through this pulley. That's really crappy. And somebody down here is pulling at a constant rate. They're going to pull that bucket up. And they're going to pull it clear to the top, which is 20 meters. It's going to go up like that. It's going to raise it up, and it's going to be pulled up at a constant rate. We don't know what the rate is, but it's being pulled up at a constant rate. So if I had just the bucket alone, and there wasn't even a rope attached to it, somehow or another, the bucket was able to be lifted by something, and it just got lifted up 20 meters. That one is, because it stays constant. The force, which is the weight. The force is the weight. Get that into your head. The weight of the object is the force, and work is equal to force times distance. So if the force, which is the weight, does not change on the way up, as in the case of the bucket, then we can figure the bucket by just taking the 22 newtons that it weighs times the 20 meters we wish to raise it, which is 440 joules of work just to lift the bucket. Okay? Because the weight of the bucket doesn't change. Now, when we do the water and the rope, we're going to have to do something with calculus because the force is constantly changing. The weight of the water is constantly being reduced. And the weight of the rope is constantly being reduced. Think about that. The more rope you pull through, the less rope you have to lift. So it's changing too. You with me? So these two are going to be based on some sort of change. So the question is, the part that we've got to do for the water, this was for the bucket. This is for the water. This is what we're going to do now, right down here. we got to come up with an equation that we can integrate, because I just talked to you a few minutes ago about that the work done here, because the weight is changing, we've got to use an integral to collect it. The work's going to be some integral. What do you suppose it'll go from and to?
0 to 20.
Good. That's the distance. The distance is going to go 0 to 20. And this over here, the distance that we're going to raise it, each little teensy weensy distance is going to be dx. But what the heck is this going to be? Just remember that the water right at the beginning started out with 70 newtons of water. By the time it got up to here, there are 0 newtons of water.
70 minus X. No. Maybe.
And to you, what is x?
X is the amount of water you're losing. Like, that's the constant rate of how much is.
And you think 70 minus x, where x is the amount you're losing.
Yeah,
Per what?
per unit of time.
There's no time in this.
Per distance,
A person.
But yeah, per distance, yeah. That's
Oh, per
Not
distance.
lost per dx.
Oh, that's a good idea. How much water was lost per meter? Maybe.
because the constant.
That might be a good idea.
Because it's going up at the same time. So
Yeah, it's going up at a constant rate. We don't know what the rate is, nor do we care. Because see, in physics, power depends on time. Work just depends on getting from here to there. Could take you centuries to do it, same amount of work. So time is not in this, but distance is, and you're right, that's what x is, because it's little teeny tiny changes in distance. So x is the distance that we raise it, and the amount of water left in the bucket is related to how far we've raised it, right? I mean, if you raise it halfway up, you got 35 newtons of water left. That's because it's going to be empty by the time we get right as we get to the top, right? If you're only going to go a quarter of the way up, you've only lost a quarter of the water. So help me write an equation that we can use for this.
At least minus 7 hazard? No. Can you take that 75 by 10?
Let me try to steer your direction in a different direction. You steer your thinking. Isn't an integral, which is what we intend to use here because we have a varying force. Isn't an integral usually, we find that we associate that with the area under a curve? What curve? This one. We don't know. What would the graph of the amount of water in that bucket look like? It would be linear
Start going.
because we're losing,
Be negative.
the hole is the same size and the thing's going up at a constant rate. It would be linear. What kind of line?
Negative.
Negative and start plus 70.
Negatively sloped line, right? So we could go to the idea of an integral being a graph. If we were to graph the amount of water, that seems to be a little more instinctive to you. You've been doing that longer. So right when the distance, remember, x is the distance. This x-axis is distance. Distance that the bucket is lifted. This up here is water in the bucket. B-U-C-K-E-D. Okay, that's the amount of water in the bucket. So before we have lifted it anywhere, how much water is in the bucket?
70.
So if I put a 70 up here, that would be where it starts. Right? What shall I put on the x-axis?
Meters.
How many?
20.
20.
Because then at 20 it'll intercept because
And
there's no
that's
water
gonna
in
be
the bucket.
0.
Right? If I go out 20 on this, then how much water is in the bucket?
None.
None. 2 points make a line.
Mhm.
Okay. The question is, this integral wants to find this area. Right? So we could, without the integral, we could just find the area by taking 20 times 70, cut it in half. We could do that without the integral. But let's pretend we wanted to use the integral. So what we need now is the equation of this curve, which is a line. What's the equation of that line?
Negative 7 half x.
70
Plus
minus,
negative
yeah, 70 minus 7 half.
What's the slope?
7 negative 7.
Rise over run,
Which is,
70 over 20.
so it's, so 7 halves, right?
Negative.
Or is it,
Negative.
it's negative because it's coming down.
Plus 70.
X, because that's where we put our slope is with the X, right?
Mhm.
Plus,
Plus 70.
plus 70. Would that be okay? So I have negative 7x over 2 plus 70, or you can write it 7 halves x. I don't care. It doesn't make any difference. They're the same thing. So what is this integral? And if you want, you can use your calculator or you can anti-derive.
That's 700.
Because it's this, that's the most important part. Doing the integral, if I make you do it by hand, it's just drudgery. You can do it because that's just linear. But, so I don't care that you show me how to do this. I want to know what this actually is. What is it? 700 joules. Okay, so far we've got 1140 joules, but we still have to lift the rope because the rope weighs something. And right at the beginning, it weighs the most. Okay, so I'm gonna put a line here. And this is going to be the rope lifting that. And it is a varying amount too. So the work done lifting the rope is also going to be an integral from 0 to 20. Use what you learned there and here. Do you think that the rope will diminish in weight linearly like the water did? Every time you pull a meter of that rope through the pulley, you have 0.4 newtons left to lift. So it seems linear to me too. What would that be? I mean, take a look and read the words there and tell me how the rope is going to apply here. And do you want to draw another graph? We could.
It'd be the same as that one, but you can start at 0.04 and go to 20.
No, because it's square meters.
Because
You times 0.04 by 20 to get the total length of the rope.
By the way, this was the weight of the water in the bucket. Maybe that'll help you a little bit. This is the weight of the water in the bucket. So if we were to draw the same sort of graph for the rope, what would it look like?
it starts at 8 newtons.
Okay, so 8 instead of 70?
Yeah.
Okay, and what will it finish up? How much rope we got to pull through when we're done? We'll be at 20 and there will be no more rope. It won't weigh anything at that point. The rope that we still have to lift, right? You know what I'm saying? What is that equation? Negative 2/3 x. 2/5.
Yeah.
2/5 is 0.4. That's what they're telling you about the 0.4 per meter. They already told you that, but we can figure it out too, because it started out at being 8. 2/5 x plus 8. So we do that the same way. It's just that the rope started out weighing 8, weighed nothing at the end after 20 meters of lift, which means that the slope is negative 0.4. They told you that in the words. But you can figure it out too. They wouldn't have had to tell you. What is this? No, just joules. So if I add them all up, I get 1220. 1220 joules of work to make this project happen.
So that's really how you do it? You
Yes.
just add them all together? You don't
Yep.
need to-
It's just a sum. 2 of them had to be figured with an integral because 2 of the weights were changing as we pulled it up. 1 of them could be figured directly because the weight wasn't changing. The bucket weighs the same top to bottom. You see the difference? Any questions?
So if there wasn't a leak,
Then we could figure the weight of the water with just a straight shot. That would just be force, which is 70. That's what it would weigh times 20
okay,
if it didn't leak.
yeah.
How would things change if it leaked, but right at the top it still had 5 newtons of
Hancock,
water?
Wyatt Staker, Chloe Gibson, Aiden Pickle, Noah Carlisle, Matt Taylor, Chandler Mott, Tucker Brown, and Jarrett Mason. Come to the office, please.
How would this be different if instead it said it didn't just finish leaking right at the top? By the time it got to the top, at the moment it got to the top, it still had, let's say, 10 newtons worth of water left. How would that change things?
Which one you put it?
Yeah, this thing at 20 would be up here at 10, and it would go down to this point, and it would be a trapezoid, and you'd have to figure out the equation of that line using rise over run. In this case, it would be 60 over 20 for the slope of your line, right? Still with 70 to be at the beginning, but it would be coming down a little bit slower. Or in other words, if you like geometry like I do, I would draw a trapezoid. This would be 10, this would be 70, and this would be 20, and I could find the area of that. I wouldn't need an integral at all, but it's the same concept. I've got to find an area. Well, you could write the equation of this line if there were still 10 newtons of water left.
Oh, there's the tiny.
If there were still 10 newtons of water, it didn't leak fast enough,
Gotcha.
then you'd have a trapezoid to find the area of. Or the area underneath this line from 0 to 20 if you can write the equation of that line, which is not hard. Slope is rise over run. And the beginning amount is still 70. It's just that your slope will change slightly. Y'all see that? Okay. You'll have to play around with ideas like that. You may want to come back and look at this or look at the video or whatever if you remember how to do it. Okay. The next problem we have also involves work. But you're going to have to put this in a different file in your head because this is a different attack. This is a different way of doing things. Still, work is equal to force times distance, but it's going to be pretty bizarre. So stay with me. Okay, here's our scenario this time. In example 3, you've got a picture to the left there. I'll draw it up here in just a minute. It says a conical, meaning a cone-shaped tank, in this figure that you're looking at is filled to within 2 feet of the top. We're going to say 2 feet down is where the fluid starts, okay? Not within. That sounds like an inequality, but it isn't. And it's filled with olive oil. The thing that's really crazy to me about this is we're talking about pounds per cubic foot. That means the linear measurements are feet. It's a big tank. This tall as this room. And really, really wide, filled with olive oil, or at least up to 2 feet from the top. That's not olive oil. It's important to know what it's filled with because olive oil has a different density than water, has a different density than mercury. Okay, so it's important to know what it's filled with. A cone-shaped tank filled to within 2 feet of the top with olive oil, weighing 57 pounds per cubic foot. Anybody know what water weighs per cubic foot?
Probably all of us. Like 60.
No, that's a little over 62.4. It says on the other
It's
page.
more because oil comes to the top.
Kyle, do you not know the thing where the oil floats on top of the water?
Oh, that's right,
The
yeah.
water's more dense.
Oil is less dense than water, but not by too much, and you're right, 62.4. Okay? All right, it says, so we've got the oil, they gave us the density, and it told us what it weighs, and it says, how much work does it take to pump the oil to the rim of the tank? The reason why this one is different from the one we did before is because on the one they did before, they told us what the objects weigh. They're telling us what the density of oil is, but not telling us what it weighs. We've got to figure out the weight in order to use force equals weight times, work equals force times distance. Remember, force is weight. Force is weight. And so the way we're going to do this and use the calculus to do it, see that funny little red disc in the middle of that cone? We're going to call that a slab. That's a slab of oil. Okay? We call it a slab of oil, and the thickness of each slab is, guess what?
Yes.
No,
You are.
be wide,
Oh, easy.
because they're stacking them up vertically.
Okay.
Okay, so yeah. No, most people fall for that. Don't worry about it, Brian. But as soon as you, what's your name, Kyle? Okay. All right, so notice on the tank that's been drawn here, how tall is it? The tank? So this distance from here to here is a constant 10 feet.
They didn't tell us that from, are we just making assumptions or?
Kyle, the diagram.
See the diagram?
The diagram is like used for our use, it's not there.
Yes, absolutely. It's not for something, it's just, yeah, for this problem, it's 10 feet high. And what is its radius? Pardon? 5? Oh, that's nice. That's a 2-to-1 ratio. That should be easy to work with if we need to, and we will.
It's almost 5.
What?
Kyle, I promise the diagram is on.
Yeah, but what? Oh, duh, yeah.
Okay, good. What is this distance from here to here?
10 minus 20.
2 feet from the top. So we've got 8 feet worth of oil. Okay? All right. Now, we are going to try to figure out how much work it's going to take to lift. This is where the calculus comes in. This is where it starts to gel with your mind with an integral. We are going to lift that slab, which is dy thick. Then we are going to lift this one, and then this one, and then this slab, and we're going to get all the dy thicks all the way to the bottom, all those slabs, and we're going to get the integral to add them up. But how are we going to use this? The fact that work equals force times distance. Let's say that we are going to do, we're going to just lift one slab, just one. And I'm going to do the representative one that they've got. Here's a representative one of the slabs. And we've already agreed that it is dy thick. Question is, oh, by the way, how far are we going to lift this thing, this slab? How far have we got to lift it? Okay, now here's the idea. First, understand this. We only need to lift it to the rim, because if we've got a hose down in here, a pipe clear down into the bottom, and we are pumping things out, all we have to do is get it to the rim, because then gravity can take over and put it in the truck, if that's what we're doing with it, loading it into a truck. You with me? So we only need to get these things. We only have to do enough work to get all of these slabs to the rim of the tank. So how far am I going to lift that slab? How far have I got to go? I know you can't come up here and draw, but the answer is this far, right? That's how far we got to lift it. How far is it from here to here? Why? How far is it from here to here?
10 minus y.
10 minus y.
Now we just need to figure out what y is. Oh wait, no, we don't. We just thought that.
Okay, so we now know how far we're going to have to lift each slab. If I'm lifting this slab, this distance right here is still y. The distance I got to lift it is still 10 minus y. I've got to lift it a little farther, but y. You see what I'm saying? So that takes care of this part right here. The force, remember, force for these problems is weight. Question now is, how much does that slab weigh? I'm going to keep track of this. Distance is going to be 10 minus y. Force, which is weight. Weight of what? Weight of the slab.
Which would be the density times volume. Density times volume. So.
I'm hearing all sorts of things. Speak up. Tell me what you think, and I'll shoot you down if you're wrong.
Density by volume.
What's that?
Times volume.
So
Volume
Times density.
times density. That's why it's important that we understand we're lifting oil and not water.
3 and
Wouldn't it be nice to know how many cubic feet are in this slab? And then we would multiply it by 57. That'll tell you what it weighs.
57.
Do you agree or not?
Yes.
So to find the weight, we would take the volume of the slab and multiply it by the density of the substance. So in this case, that's 57. But what's the volume of that slab?
The integral from something to something.
Pi r squared h, because that slab is a cylinder. Very short cylinder, but it's a cylinder, isn't it? Pi. Now, what is r? I need to know the radius of this slab to figure this out, to figure out the volume. What is this?
Y halves. Y halves.
Isn't it 2x?
No, y
It
halves.
would be y half.
Yeah, it's half of y.
Oh, I guess.
You guys can't see it. I'm like the catcher in a baseball game, like I told you before. But I said that. I said, yeah, it's 1/2 y. And you should have seen. I tell you.
I don't get it.
She goes like this. She's going like this. She goes. It has to do with this ratio, Natalia, 10:5. If this slab is y units up, then this radius is half of that.
Okay.
Because that 2-to-1 ratio maintains all the way up. Do you all understand that? You're getting that? I like her body language now. She was going, no, she's going, yeah. All right, it's good, it's good, it's good. So this radius is 1/2 y squared. And how thick is it? dy. So here's what I've got here in the force, the weight, all of this weight thing that I had to figure out. I've got pi fourths. Do you see the pi fourths?
Yeah.
Pi fourths y squared dy. That's my weight. That's my distance.
You forgot
Times 57.
What?
Times 57.
Oh yeah, times the 57. So I'm going to put that right there. Is that okay? Thank you for that. Cool. All right, so the integral then to figure out work is equal to the integral from where to where?
0 to 8.
Is it 0 to 8?
Be 0 tenths of the rim. You have to get to the rim. Oh, we got controversy.
Where's-
dang it.
John, you tell us why you think it's 0 to 8.
Because that's all like adding up all the different weights
Oh,
of the silt.
Because that's all the longer the slabs last.
I've been converted.
The slabs are what we are gathering with the integral, and the slabs only go from 0 to 8. Where does the 10 come in? So we are going to collect slabs from 0 to 8, and it's going to be, I'm going to back this off a little bit because I want to put some constants out here. It's going to be 57 pi over 4, and then the inside is going to be y squared times the distance, which is 10 minus y dy. You get it all figured out. That's pretty simple integral. That's just a polynomial, which you could integrate if I made you without your calculator, which I'm not going to because it's the setup that's important, like I told you. So once you get it to there, you grab your calculator, and it's like preparing a room to paint, like I told you yesterday. All this crap here is all this drudgery and getting into it and being confused. And once you get to here, now you just coast along.
It's a big number.
It is a big number. It's a lot of oil. How much is it?
30,051.4.
What?
13.
What? No. Okay. I'm okay to get around to there. What's the units? It is foot pounds. It's not joules. How come? Because the oil was told to us in pounds per cubic foot, and the measurements on the diagram were in feet. So we've got to go to foot pounds for the work. Okay? How we doing? Do you understand how this is different from lifting the bucket and the water? The reason why it's different, this is different from that, is because, like I said, on the bucket and the water and the rope, they told us how much things weigh. We didn't know how much things weigh here. All they told us was the density of the oil. We have to find the weight of the slab. We're still using this as a fundamental thing, but this time the weight we have to figure out. It's the weight of a slab, which is the weight of a cylinder filled with a certain density stuff. That's this. And we have to lift it to the edge of the rim. And if that slab is y units up, then we have to lift it 10 minus y more feet. And that gathers all of them together. It's magical. You okay on this? You see how it's different from the first one?
Yes.
Okay, it's still, both of them are still based on this, but this one you had to find the weight on it yourself. We okay?
Yep.
All right. Now I got to talk to you about some more physics. So this isn't a physics class, but you're going to learn some more about physics, and it has to do with pressure, water, fluid pressure.
When we get the great molasses crisis.
You've all, I'm almost certain anyway, that all of you have experienced being in a pool, going down really deep and feeling your ears hurt. You felt that?
Yeah.
Okay, and it happens at about, for most people, it happens between 10, 12 meters, about that. You start to really thump on your ears. You can acclimate to it if you spend a lot of time in the water and you go deeper and deeper and deeper, you can handle that pressure. The other thing that happens when you go really, really deep is your lungs can't expand as easily. Do you know how your lungs expand? Do you know how they actually expand? What causes you to breathe in? Yeah. There's a diaphragm down here and there's muscles on it, and that they pull that diaphragm down like a piece of rubber at the bottom of a deal. They pull that down, creating a slight vacuum in this space up here, and it makes you go, it wants you to fill that space with air. Did you know that if you took a pipe, like a snorkel, about that size, put it in your mouth, and it was really long, went way, way, way up, did you know that you can only go a meter under before your diaphragm is not strong enough to create that small vacuum and die? People go a lot deeper than that. And yes, you do too by holding your breath. But if you're going to go more than about a meter down and try to breathe through a hose by having your lungs expand, by the time you get down just below a meter between 1 or 2 meters, the pressure from the air coming in on your lungs is too much for your diaphragm to cause that expansion. Can't do it. It can't do it. That's the reason why they don't send people way down deep with hoses that just go up to the top and breathe through the hose. They don't do that because they know it's not going to work. But how can people go really deep? They wear tanks on their back, And yes, the pressure increases on your lungs and your body, it shoves everything tighter, tighter, tighter. That gas is under pressure. All you have to do is bite down and release it, or shove it in your mouth and your lungs.
Oh, that sounds really fun.
It's under pressure. And so,
It is.
So people can do the scuba diving if they can acclimate to the pressure on their head. The other thing that you have to do, my brother is a scuba diver, and he told me this too, he goes, the other thing you have to do is do some tremendous mental discipline. Because when you get down there a ways, 25 feet, that's pretty far, really. Get down there 25, 30 feet down, you, your lungs, even with the air being shoved in with pressure, your lungs still can't expand because the water's pushing in so tight and your lungs can't open up as much. However, you're still getting the oxygen you need because it's enriched oxygen. And so your systems are still operating fine. They're still getting the oxygen they need, but your lungs are used to expanding. And you have to mentally talk yourself into believing and tell yourself, I'm getting the oxygen I need, even though I can only do this. That's all the farther your lungs are allowed to expand with that pressure. And it's hard to talk yourself out of panicking. Anyway, I've never done it. My brother does it. He tells me all these things. Okay, so what we're talking about here is fluid pressure. The farther down you go, the more pressure there is, and it has absolutely nothing to do with how much water is being backed up by a dam, for example. I've got, have you all got, I'm sure you've been to a dam, Palisades, Ryrie, Ashton, something, you've been to a dam, right? And it's holding back a whole bunch of water, miles and miles and miles of water, usually, when they put that down. And it backs it up as far as the riverbed goes up to the top of the dam level, and then it spills off into other places. But it backs it up that far. It has absolutely nothing to do with how many miles of water there's backed up. Now, I want you to try to imagine this. This is a mind experiment. If you had a bulldozer that was shaped like the riverbed, and the riverbed is perfectly shaped, parabola, half circle, I don't care what it is, but you've got a bulldozer and there's just a little tiny bit of water on the floor of this dam. It's perfectly, cement, sealed up, nothing leaks. And you've got this bulldozer that sits at the end of it and it pushes all the water. It gathers it from the bottom of it, gathers all that water up and pushes it up against the dam until the bulldozer blade is this far from the dam and the water is filled to the top. That's how much you've gathered together. Can you imagine that? The pressure from going down in that little bit of water 12 feet will be exactly the same as the pressure going down 12 feet with all the miles of water backed up. It's the same pressure. It has to do with how deep you are, not how much water is backed up. Okay, so pressure is completely dependent on how far down you go. Now, take a look at the diagram they have on page 421. They're showing you a dam there and a cross section and the water that's holding up. And can you understand physics-wise, why they would have to build a dam with that shape? If you just build it with a wall that's as wide as the top and went down like this, the pressure at the bottom pushing on that dam is way more push on that dam than at the top because it's deeper, right? So you got to build it thicker on the bottom, otherwise it's going to bust through the bottom. Do you agree? You see why they have to build dams the way they do? Over in Boise, they've got the Lucky Peak Dam as you go up into the hills. So it's built like that. Only it's just a straight. It's pretty wide. It comes down like this, and all over it's painted in green. It says, "Keep your forest green." People have tried to walk down it. It's made of basalt. It's like that stuff that you see in the Helsinki lava flow on near Blackfoot. That kind of stuff. Stones that they put and piled it up there. People have tried to go down that. You miss your footing even a little bit, you roll down that. Pretty bloody at the bottom. Back. Okay, we have a news story over in Boise once in a while. That's where I grew up. All right. So here is how we're going to the pressure. This is a simple formula, but pressure is going to be equal to the weight density. That's not a W. That's a small omega. The last Greek letter, small. Not capital, what do they call it? Lowercase omega. That stands for the weight density of whatever it is. If you're holding up oil, it won't hurt as bad to go down as if you're holding up water. And that'll really hurt if you're holding up mercury. I dare you to swim in mercury. Okay. Times, and they use H. That means, and it's kind of stupid. Usually when I see H in something, I think of height. This stands for depth. I'm not even going to put an H here. I'm going to put a Y because depth is vertical. That'll remind us what our variable is. This will be a constant depending on the fluid. This will be how deep you are in the fluid. The Y, vertical motion. The pressure that you experience at this depth will be figured by multiplying these two together. Okay? All right. So, it says do 1 or 2 of examples 13 through 16. Okay. So I'm going to make up some things. I want you to turn to your exercises right now because this is all the information he gives you to do these exercises. Nobody knows how to apply it. So I'm going to show you 1 or 2. Okay. So go to page 426 and look at 13 through 16. It has to do with this density thing. Well, not density, this pressure thing. Okay. In this one right here, it says, in exercise 13 through 16, the vertical end of a tank containing water, which is the blue, weighing 62.4 pounds per cubic foot, that's your density, has the given shape. This is what we are to do with these different shapes of tanks. Explain how to approximate the force against the end of the tank using a Riemann sum. You won't have to do that. You can go right straight to the integral. We don't have to do the Riemann sum first. We're going to talk about it, but we won't actually use it. Then B says, find the force as an integral and evaluate it. So we'll do just the B part. So what we've got there is some sort of a trough that somebody's got there, and let's say it's shaped like that semicircle. It's a semicircular trough like this. Boy, that's a crappy semicircle. Let me come down a little ways. About like that. And the trough extends out like this. And I don't care how far the trough extends out, because the pressure will be determined by how much I fill it up. This is like saying the amount of water backed up by a dam is irrelevant. It's just how deep you go. So I don't care how long this is. I want to know the pressure, the total pressure. No, the total force. I haven't talked about that. The total force pushed on the end of that tank by the water when you fill it up. The total force. We haven't talked about force. We only talk about pressure. Force. How do we convert this to force? How do we talk about force on a total? And the answer is, I can't remember. Got it. Force, this is pressure. Force, when we're talking about force on the end of a tank, not work, no work's being done here. Nothing's being moved. It's just force on the end of a tank is pressure times the area over which it is applied. This is the reason why when, and I don't know if guys have experienced this or not. I mean, we have to be anti-sexist all the time, but I think it's happened to most girls. If you're wearing high heels and you're walking across the lawn trying to get to your church meeting because you're late, they sink in the grass. Whereas your boyfriend that's running alongside you or your brother who's not wearing high heels has no trouble. And that's because his mass or the force, his weight, is spread out over a greater area. Yours isn't. Yours is spread over this little tiny bit here on the top and a little tiny bit on the high heel. And this much smaller area, you sink. That's what we're talking about here, is that force is equal to pressure spread over an area. Okay? All right. So now the question becomes, okay, if we want to find total force on the end of this tank, don't we just take the pressure, which is the weight density times the depth? Ooh, where's the depth come into this? I realize there's more pressure the farther down I go. If this is 0, we'll say. And we're going to go down this way, and this will be a positive number down. As we go down, it's going to get more and more pressure that way, but area of what? Area of this semicircle? Because the force applied to this part of this semicircle is far less than the force applied to this part of that semicircle. But the force applied to this piece right here is the same all the way across because that piece is the same depth down. You follow? So what I'm going to do is I'm going to use, to figure out the force, I'm going to use an integral to gather up this little force applied over a larger area here, and the force applied to this one, and the force applied to this one, because the force changes the deeper I go, because pressure changes. Pressure gets bigger as I go down. So I've got a changing force, and I will use an integral to gather them all together. And it will go from, in this case, I don't actually want to do number 13, so I'm going to put my own dimensions on here. I'm going to pretend this trough, I'm going to pretend, how deep is it in the book? Okay, I'm going to make it 5. So this trough is from here to here is 5 feet deep. So I'm going to put the thing down here, I'm going to put a 5. So it goes from 0 to 5 down this way, and that's the depth. We'll pretend that actually touched, okay? So it goes 5 feet deep. That's this distance here. That's the radius. But I'm not interested really too much in the radius. I'm interested in a representative strip. How wide do you think that strip is? dy. And what I'm going to do is I'm going to figure out what the force is on this strip. And then I'm going to make this gather them all together for total force. Okay. Can you see that the area of this, the area of this strip, if I draw it out here, the area of this strip is its length times dy. Yeah? And that would be this A right here. It's just the area of the strip. And the pressure will be the 62.4 times however deep I am, which will be y. You following? Are we already out of time? So this distance from here to here is y. That's how deep the strip is. What? No, seems like the only thing missing here is how am I going to find that? Because it's different. It's widest here, and there's a little bit. And the answer is the equation of the circle. That's what it is. So if I want to find out this point right here, wouldn't this distance from here to here be the x coordinate of that point? And same back here, so I will double it. This, I would really like to know that point right there. Well, they have this circle. This circle's equation is x squared plus y squared equals 25, which means that, now I want to solve for y or x? X. I want to solve for x. X is going to be the square root of 25 minus y squared. You see it? Which means this length is 2 times the square root of 25 minus y squared.
Where's the y2? Doubling it.
Because this distance is all I've got with that x coordinate right there. This x piece right there, that's x. I've only got half that strip.
I got it.
Okay, so here we're going to pile it all together. We've got P, which is weight density, 62.4, times the depth, which is a variable, times, that's my pressure right there. That's my weight density times depth, times the area, which is 2, times the square root of 25 minus y squared dy. From where to where? 5. Those are the stats where I'm collecting my strips from. Crazy, but that's how you figure total force on that now, is because it is pressure, which is weight density times distance or times depth. So that piece right there is right here. There's your weight density times depth. That's right there. Times the area. Area of what? Not the area of that semicircle, the area of a strip, which is 2 times this dy. Length times width. It's all there. See it?
Yeah.
Okay. We will come back and finish this tomorrow. We're out of time today, so.
Wait, why is it 0 to 5 if 5 is like below?
Yeah,
Because we're inverting things. We could go from 0 to 5 this way and collect them as we go up, but that would make your depth have to be a negative. On these problems, you want to go where the pressure is 0 to where the pressure is greatest. Just trust me. Just trust me. It keeps everything positive. Yeah. All right. That's it for now. I'll get the other one tomorrow.